this is Andrei Vanescu from Fitbit again, and I'm going to present now NuttX in a flat memory constrained environment. The background for this is I was known for a while as the memory guy. Before our launch, we had a lot of memory optimizations to do on the first tracker in the Fitbit, in the NuttX line. So let's start with the case study of this device. So this is a Charge3 special edition. It's an NFC-enabled tracker Fitbit launched in November 2018. While there were many memory optimizations on the Charge3 Simple as well, the second edition brought along the NFC subsystem, and this required even more finesse. As a Fitbit tracker, it logs steps, flights of stairs, heartbeats per minute, and various exercises activities the user has done. This data is displayed to the user on a grayscale screen that you can see here in the picture, but it's also encrypted and sent to our servers, where they are further processed to be presented in the Fitbit mobile app to the user. So to accomplish these, the device has a BLE transceiver and a dedicated core to handle the BLE connection, an NFC chip, several sensors from an accelerometer for steps, an altimeter for stairs, and an LED array on the backside with a specialized analog to digital conversion chip for multi-channel programmable acquisition or photoplethysmogram, PPG, which measures heart rate. As a user interface, there's a grayscale display with double axis touchscreen, which enables both clicks and vertical and horizontal swipes. This is rounded up, with a vibe motor, which has configurable patterns and an inductive button that you can see on the side. So the case is metallic, and you just need to squeeze the case a bit, and you trigger an action. It's not a physical push button. In addition to passive monitoring, the device can also display notifications or calls from a smartphone, set alarms or timers. There's a guided breathing app, a weather app, and an exercise app that lets users do workout sessions, runs with their smartphone's GPS, and a few more exercise types. The tracker doesn't need a permanent connection to the smartphone, as it can hold multiple days of data. It will hold a charge for 7 days. So the main challenges are the overall small memory footprint, especially when put side by side with a list of features. It has to have a rich UI with animations. It has to have swipe transitions. When considering the total memory budget, a lot of that just needs to go to the UI, since just the frame buffer is 10 kilobytes of RAM. It also needs to support a lot of languages, some of which have a large number of character sets, actually character sets of large sizes, which need to be cached in their rendered shape in different font sizes. So it supports Chinese, Japanese, Korean, and so on. You may ask why limit to 300K of RAM when external RAM chips are easily available. And while it's also a matter of cost, the small form factor is also a big challenge, since there isn't a lot of room inside the case once all the components are in. And the final challenge is the 7-day battery life, but this is outside the scope of this presentation. It mostly revolves around managing the big consumers in this tracker, which are the display, the vibe motor, and the flash memory. So as I mentioned before, our 300K of available RAM needs to be split between several features. This is an approximate chart of that distribution. It considers static memory as well as base dynamic items being allocated. It doesn't account for various peak usage scenarios of various subsystems. For instance, NFC can spike quite a bit when doing certain operations like adding a card to a secure element. One of the first things we note is that our system is a flat build of the NuttX kernel. So we did not have enough memory to have two independent heaps. So normally, if you would have had two heaps, one for kernel space, one for user space, we wouldn't have enough memory for extra buffering, free space in both, and to account for fragmentation in both heaps. So right now there is only first-party code running on the tracker, so we don't have to worry about malicious behavior. But one of the downsides of having a flat build is that we have to be extra careful with memory corruptions, since the kernel and user allocations are intertwined. The categories already listed here are fluid and are mostly for the purposes of this presentation. A lot of auxiliary memory, like stacks and driver buffers, are called out specifically instead of being allotted to their respective categories. In essence, I could have marked like the frame buffer driver memory as part of UI instead of putting in the drivers, but I thought it's more informative this way. I'd also like to point out that 25% of our system is statically allocated and the rest is all heap. So let's dive into what the UI uses the memory for. So our UI is based on XML-like views that generate every screen. And these have to be cached in memory while operations on it are done. So that's some memory there. Rendering output itself is done to the frame buffer. A lot of UI memory is also used for the font engine. We keep parts of font files in memory so that the font rasterization can occur quickly. And we cache those generated glyphs, since rendering is an expensive operation. The glyph cache itself is the biggest chunk, and you can understand quickly why it has to be a large chunk, since if you want to scroll through a large portion of text, you have to have all the characters ready. And this might be easy for any Latin language, but it's next to impossible for any of the Asian languages if there's a lot of characters on the screen. So the second largest category in our pie chart is the file system. A big chunk of that is the logical physical mapping in SmartFS, which is a Flash-based file system for weather leveling. It requires this translation to maintain the same logical indexes for sectors, all while relocating the other physical locations when the memory is changed. You can also see Julian's presentation of this topic. It was previously here on this conference. Of course, you don't necessarily need this mapping. An alternative approach would be to do a search for a physical sector throughout the Flash every time a logical sector is needed. But this is too slow for most applications. This means that the mapping is mandatory, but we've found a way around it with partial mapping. Additional memory is spent to deal with open files, and open files require a buffer to write to before data is flashed to storage. And while this was initially allocated as one buffer per open file, this was too much. And we now operate a cache of such buffers operating on least recently used. There's also a smaller MTD layer cache with one element that speeds up some of the operations. The main separation of functionalities in the system is done at a task level. And as such, there are plenty of tasks at any time in the system. Which tasks are active is dependent on the run level. We have an init task, a shell, sensor task, a UI task. There are also tasks that are mapped to middleware software threads. Those are required for some of our external components like NFC and touch. The vendors have their specific middleware. There are also worker threads, and of which one of them is the event-based worker task, event D. Stacks in general can be as small as 900 bytes, but can work up to 4K. And we generally allow about 200 bytes of buffer space on top of their maximum recorded usage. We have additional protection that I'll discuss momentarily. So our general approach to memory was to consider the uses for it and take into account the time aspect. When does this need to be allocated? When am I going to read from this? We have established a few memory usage patterns and their respective allocation time. So for instance, for continuous use memory, of course, we will use statically allocated memory. If we had a lot of memory available with the same access speeds, of course, this could be extended to more and more categories. The most stable system is one that just has static memory and doesn't allocate anything. It will definitely not have any memory problems, but it's probably wasteful. Heap memory, on the other hand, is dynamic, of course, and it ties into dynamic usages. For instance, you have more open sockets, that means more socket buffers. And of course, you can put this in static memory if you were to do more planning around how many buffers you pre-allocate in static memory, but that's also, as I said, wasteful. So mostly use it for dynamic uses, transient ones, and I also added transmissible because any information passing in a flat kernel build that doesn't do a deep copy needs memory that isn't on a stack. For stack memory, we're left with small items that are needed in the current function or in police of that function. So in functions being called by this function within the same task. So here, why do I say transient? Because memory on near the base of the stack has almost the same lifetime as the task. For instance, if you have a local variable in your main function of the task, it will be there forever. But that also means that it needs to be passed along as an argument, which could end up taking even more stack space if the number of parameters is being passed are more than 4. On ARM, the ABI says that any parameter over than 4 is usually occupied on the stack. On the other hand, memory that is allocated near the top of the stack is inefficient in terms of occupied memory, since the stack has to be allocated to handle this maximum height, even though it's only reaching this maximum maybe in 0.01% of the time. So for instance, if you have a large allocation right at the top of the stack, let's say the leaf function has 1000 bytes, then you have 1000 bytes more in the stack of this task for nothing, because most of the time you will not need those 1000 bytes. You'll just need it when that function gets called and the maximum is reached. There's another reason why you should keep these allocations small. That's because the compiler doesn't optimize very well for total stack height. And sometimes it actually increases the stack height when optimizing. So GCC modifies the stack with the maximum height needed once per function, since it's more efficient. So at the beginning of the function, it will say, move down the stack by 100 bytes. So the effect becomes compounded if unlikely paths uses. Sorry, I lost. Yeah, so there are, it brings down the stack by 100 bytes, but if unlikely paths use a lot of memory, then you end up having this every function. So for instance, if any function can be a leaf, but also call other functions, it will bring down the stack more and more and more, because GCC doesn't care that you won't take that branch, it just gathers the maximum. So if there's an unlikely path in each of your functions, having a big buffer, it will increase your stack size by a lot. So let's say that there's an error handler which again, allocates 1,000 bytes. And you always say, if something wrong happens, then allocates 1,000 bytes, then annotate something. And this means that every function you have will have 1,000 bytes on its stack. And this means that eventually you'll run out of memory. Okay, so overall, our approach was to aggressively move things to the heap and to the stack where possible, but this produces two big problems that I'll talk about from now on. One is heap fragmentation and one is stack overflow. So this brings us to our modifications to the heap allocator. The NuttX heap allocator is generally great with how it handles fragmentation, since it always merges adjacent memory chunks when freeing. Unfortunately, there are limits to the system. And when smaller allocations have a longer lifetime, and I have plenty of examples of this, for instance, polar structures, IPC subscriptions in our pub subsystem, inodes, file structures, and so on. Those will be small allocations, but will have a longer lifetime. In terms of memory overhead, it's also quite good because it only adds 8 bytes per chunk. But we made note of our maximum memory, which was 300K around. And due to the fact that heap nodes are aligned, we managed to fit the sizes in 16 bits. So we cut down the overhead by 2. And we were still able to have 256 kilobytes of chunks in the heap. The gains just from decreasing this overhead was about 2% of our total memory usage, including static memory. So it was a big win for a very small change. So what about heap fragmentation? Because I've talked about it, but I haven't said how we addressed it. This is generally observed in NuttX by checking the largest free chunk over the total free size. So with a ratio of 1.0, memory is perfectly unfragmented. You have 5 kilobytes of free heap, and there's a chunk of 5 kilobytes ready to go. We found it common to observe about 0.5 and above, meaning that you have 5 kilobytes available, but the biggest chunk is only 2.5 kilobytes. Some scenarios that we usually run could stress the allocator and produce much lower ratios, 0.25 or below, which would bring us closer to running out of memory. So after taking into consideration the histogram of our allocations in the system, we split the heap into 2 heaps. A small heap, which handled exclusively 16 or 32 byte allocations, here on the left, and these would overflow into the larger heap, which could handle all allocations. So large allocations would go directly into the large heap, and small allocations would go into the small heap until this was filled, if it was filled, and then it would go into the large heap. And this brought our fragmentation problem to an end because we were able to keep fragmentation ratios of much higher, even in adverse scenarios. And by adverse scenarios, I actually mean run level changes, because why would the heap allocator be stressed? So because we don't have enough memory to do everything at once, we rely on a subset of tasks being active at one time, with an example in this figure with fewer states. And we use Runlevels to achieve this, starting and gracefully shutting down tasks as certain functions of the device have to be accomplished. For instance, downloading a new firmware and installing it. This means that entire groups of tasks with their stacks, TCBs, associated memory, are being allocated and freed at once, which is challenging when most of the heap needs to be used and it's close to being full. So imagine everything being freed, and then suddenly you want big chunks, you want small chunks, you want everything that wants to be filled again. So I've talked about fragmentation, and now let's talk a bit about Stack Overflow. Because adding local variables invariably leads to these overflows. And the way tasks are created, stacks will by default overflow into heap chunk metadata or in actual task metadata. So for instance, when you create a new task, you create the task TCB struct, a task group struct, and then the stack. And of course, the stack rises this way and it overflows into the task metadata. This can lead to deadlocks due to tasks being compromised or asserts in the heap allocator, because the heap allocator will notice that there's something wrong with the metadata. This is the happy case because in unhappier cases, it will be much more difficult to identify and solve. And since this is easier to generate than to identify and solve, we added several mechanisms to help against it. So for instance, we use stack canaries to monitor how much each stack has used from its allocation space. And since the stack has to have the canaries, we see immediately how much of the stack it has used. Of course, this doesn't protect us against stack overflows, but it does give us an indication of average and maximum stack usages, which we can then use to adjust stack sizes. To actually protect against stack overflows, we've enabled the MPU in the flat build that we have to protect the end of the current stack against writes. So every time you do a context switch, you protect the stack of the task that is currently running. For instance, an MPU region here of 128 bytes protects against functions that use at most 128 bytes of stack. A function with 500 bytes of stack could very easily write beyond that. And for that reason, we also have a runtime check that assures that we don't go below the MPU region size. So these changes guarantee that stack overflows are being caught in a flat memory environment with a high profile, easily identifiable crash. So in terms of files and storage, more than 10% of our budget is spent on the file system. We mostly have several open files for sensor records, and these are large files and you can't close them and open them up between writes because the actual seek to write to the correct index takes very long. So in our case, it was more efficient to keep them open. And since it's important to keep them open and not necessarily keep their sector buffer allocated, we modified the implementation to instead use a cache for sector buffers. We also optimized a lot around the sector map, the S-map structure that you can see in Julian's presentation. There you can basically mount a SmartFS file system without being able to access all of the files, but with reduced RAM usage. So what are the broad categories of memory optimizations that we've done? The first few passes of many that we did were spent identifying mislabeled read-only memories. Sorry. So we identified mislabeled read-only memories. We split structures that had large read-only content, and we sent arrays that were pre-allocated with a lot of components, partially or completely to the heap. We then spent some time multiplexing large usages in time, just like the partial mapping example. Also with the firmware updates. The firmware update runs with the complete version of the file system, but otherwise works with a simplified version of the UI to save some memory there. We trimmed a lot of buffers and stacks to their actual use. An example of this would be freeing socket buffers if we didn't need both directions for that particular socket. We also negotiated some feature cuts where necessary. For instance, the app and clock face install is a fairly rare process and could potentially consume a lot of memory due to its need to access the entire file system. As such, we moved it to a firmware update run level, and there's already access to the entire file system there, and there's no risk of it running out of memory. Of course, optimizing and minimizing buffer space means that memory corruptions are more likely to occur at any time. Those, of course, can't be protected the same way as we protected stacks, so we devised other methods of diagnosing them. Besides the obvious heap asserts that would happen when pointers would be invalid, we would save core dumps to flash after a crash so we could inspect the entire memory offline. We also employed special builds at times with poison values and checks in the entire heap, which were more quick to detect overflows than just letting the heap find one of these invalid pointers. What about memory leaks? With a device that runs nonstop and with not much spare memory leaks can become a big problem. Our first method of detecting these was actually statistical in nature and happened by accident. We had a lot of out-of-memory crashes in an internal field testing population, and the reported free heap was down 300 bytes every 6 hours. With the amount allocated in the time period, we were able to quickly pinpoint the offending allocation and find the leak. Surely, you cannot find memory leaks this way all the time. So we also have a tool with which we do before and after snapshots of the memory with reference counting to find unreferenced memory. So you can easily know that there was a leak. Finally, the method that was most successful, but rather costly, was to keep allocation registries per task and free memory on task exit, making sure that no memory leak occurs from an application. So this means that memory leaks can only occur from the kernel side. In conclusion, and it may come as no surprise in this audience, NuttX allows and supports low memory footprints. Of course, our system is not the smallest system ever to run NuttX, but it does pack a lot in those 300 kilobytes of memory. So what we have learned in the process is that tooling and information about crashes and the situation the device is in is key. In terms of optimizing, the law of diminishing returns applies very well. We had to optimize all along, but in the beginning, 10 kilobytes of RAM was just a config away. Towards the end, we had to modify the file system a lot just to accommodate those 12 kilobytes of RAM. And right now, we're glad if we can free 200 bytes. The final lesson was that this is easier achieved when all contributors to the code understand the price of RAM and take good care of memory when they open up PRs and make changes. Thank you. I can take questions any moment now. Okay, so question for Alan from Alan is, how do you get those core dumps from the field? We actually have to get them from a serial connection because they are quite large. So generally, we connect to the device in question and we obtain the core dump.
Okay, Andre. Um, Hello, Maju and Sarah. Do you have some questions to do or other observations we need to do now? Otherwise, I can we can finish. We have one from Abdelatif. Uh, did you had did you had the chance to try the Protect build?
Ah, sorry, I was muted.
Yeah,
So we had the protected build in the beginning, but we were unable to keep using it because of our memory demands.
you
Um,
mean it was spending wasting memory because the granularity?
yes, so right now we basically need to maintain some free memory. We don't have to partition that between kernel and user memory. It's much more difficult to know how much memory you're going to need in advance for the kernel and plan for that, and separately for the user space. And in
Yeah.
our case, it was easier to put them together and say, okay, this is one big chunk of memory. How much do we have? This amount. And peak usage is around at this amount. So we're okay. Um, there's some more questions. How does changing run levels differ from manually starting and killing tasks? Is one method preferred over the other for system stability and memory usage? Oh, well, which is Dan Howe from Fitbit. Hey, Dan. So actually, we have put in place some pre-registration and post-registration for run level changes. So there are actions which happen before and after. There's also a system where we know which tasks we need in the target run level and in the previous run, and we know which task we had available. So we can keep those running and we don't have to close everything and restart everything. So there are tasks which keep running throughout the system if they're needed in all run levels. Um, also good thing about having these functions that happen before a run level change is that we can do things like partial mapping, where we instruct the file system to go into partial mapping mode or full mapping mode. And this is done there, which, by the way, Julian hasn't mentioned it, but this is a full POSIX interface. So it's not the cleanest thing, but you do an ioctl to the driver, and then it says, okay, I'm going into partial mapping mode.
Okay.
Brennan asks, are there any tools you were using to break down the usage? We are starting to add Bloaty to the CI to do some analysis. Um, a lot of manual tools, such as manual inspection, just charts and Excels, and finding the memory is less than half the challenge. Actually, freeing the memory is a bigger deal. We also made some tools to find out things at runtime and try to find correlations between heap chunks, but we didn't get that very far with that tool, unfortunately.
Okay. We we don't have other questions.
Oh, sorry, I'll add to that a bit. So
Mm.
there are some tools which we were able to use to find out heap usage based on point of reference. Oh, sorry, from calling function.
Mhm.
And those we would index by basically folder in the NuttX repository that they originated from. So that's why I said Excel sheets. So basically tools that feed into Excel sheets that we can then pinpoint where the allocation came from.
Okay. So thank you, Andre.
Thanks.
I really appreciate your presentation and all the other guys from your company as well, and all other presentation here. But I was surprised by this many presentation from you guys, and it's I really enjoy it. And it should be nice if the Fitbit guys was in the first uh, NuttX workshop last year in Europe. It should be nice to
Unfortunately, we weren't aware of it.
oh
We
we
found out from one of our colleagues for that this one was happening, and we were very excited to join, of course. And we are happy to be here, and we're happy that you enjoy the content that we've shown so far.
thank you so
And looking
much.
forward to meeting you guys in person sometime
Yeah,
next year, maybe.
yeah. Let wait for next year. I hope 2021 is a better year for all for everybody, not only for ours in our community, but for I hope we change this page because it's a very bad situation in all countries, in all places in the world currently, and it should be nice to meet you and all the presentation, all the guys that are here watching these presentations. It should be nice to have a face-to-face meeting like we had last year. Uh, let's wait for it. Okay. Thank you so much.